Last time we looked at the perception of color. We detect color with the cones at the back of our retina and the back of our eye. We have three different types of cones. We have red, green, and blue. But we also detect color with our brains using the combinations of signals from our cones to decode, to evaluate other colors. So for example, when we see white, it's because the red, green, and blue cones are all vibrating at the same time. When we see yellow, it's because the red and green cones are all vibrating at the same time. In fact, our brains are more important in color perception than I even mentioned. Look at this picture from Greece. You could give an ancient Greek all day to describe it, and he'd never use the Greek word for blue. There's no blue in Homer's writings, plenty of red. In fact, it turns out cultures developed the word for red way, way before they developed words for green or yellow or blue. All cultures kind of evolve their understanding of colors in the same way. They apparently, without the word blue, didn't even really see blue, didn't perceive blue. It was just part of this general other color. Their brains didn't have any practice distinguishing blue from red or green or yellow or white or whatever. And so they really didn't develop that ability. It's kind of weird and it's kind of cool. And there's an African tribe that they have so many words for green, for different shades of green, that they can actually, it has allowed their brains to distinguish different shades of green much better than we can ever do. There's a set of colors, rainbow of greens that all look green to us, but there's one that's very different to this African tribe. To us, we can't even distinguish it. So the brain, and in fact language, is probably at least as important as the little cones on the back of your retina. We're really here today to talk about subtractive colors. Okay, so light comes from the sun. That's direct light, and that's white light, okay? And our eyes perceive that direct light. But most of the stuff we see, everything you see around you, all these colors are reflected colors. And this shirt is, I don't know what you call it, lavender colored. It's because the light that makes up lavender is reflected. The various frequencies that make up lavender are reflected, and all the other colors are absorbed. A red apple reflects red light and absorbs all the other white light that's hitting it, all the other frequencies. So let's talk about that and call them subtractive light, or pigments and paints and inks. You're getting sleepy. We're going way back, way back to first grade when you learned about colors. This is also a color demo. We'll talk about that at the end of the lesson. Way back. And here's your first grade teacher teaching you about colors. The primary colors are red, yellow, and blue, because you can make any color with red, yellow, and blue. And so you tried. You tried to make green. You used yellow and blue, and it was disgusting. Now we know how to make green. You use yellow and a color called cyan. And when you do that, beautiful. See, paints and pigments and inks and things like that are based on subtractive colors. Light hits them and they absorb some colors and reflect the rest. And so when you do that with red, yellow, blue, it doesn't work. But when you do it with magenta, cyan, and yellow, you can make any other colors. Just have to balance the amounts of those inks. And that's what they do in inkjet printers. It's called subtractive colors. So this is how subtractive light works. Usually you have a bright light, sun, overhead light in your room. It has a broad variety, a broad spectrum there of all these different colors. Those colors hit an object. Let's say it's an iguana. And the iguana reflects the green light, absorbs all the other lights. So it has pigments, it has molecules basically in their compounds that absorb these other colors, and the green reflects off. So if we want to draw an iguana and somebody gives you a blue pen and a yellow pen, the problem with this is if you do the yellow basically absorbs or blocks the blue, violet, and the red. Blue, violet, red, and some of the green. And the blue blocks yellow, orange, red, and most of the green. And what happens is very little green gets reflected. It just ends up being this nasty dark blotch. So that doesn't tend to work out. So those traditional primary colors don't work. But cyan, which is kind of in between there on the blue-green world, if you have yellow and blue-green, what happens, yellow basically absorbs all the blue, violet, and the red. Cyan absorbs the red, the orange, and the yellow. And so what happens is green light is reflected. This is the only one that can come. And so you end up with green light. The way inks actually work is kind of interesting. We don't have perfect cyan, magenta, and yellow inks. We just have things that are kind of close. So they have these little graphs. They're called transmittance. It's basically if you fill a tube with that cyan ink, I've done it in the past, diluted pretty heavily. If you shine white light, which remember has all these frequencies, on the cyan, some purple, some violet, I should say, some blue, and some green get through. See, so violet gets through, blue gets through, some green gets through. Okay. Similarly, if you do it for magenta, it lets through a lot of red over here and not very much green, zero green, and a little bit of purple and blue. And yellow lets through none of the purple-blue realm, and it lets through a lot of green, yellow, and red. If we want to make blue, we combine magenta and cyan ink, and the magenta absorbs all the stuff in the yellow-green range, and the cyan absorbs all the stuff in the red range. So what you're left with is basically violet and blue. And if you look, both magenta and cyan let through a fair amount of violet. The violet's there, but once again, those lower frequencies or higher wavelengths, longer wavelengths, our eyes are more sensitive, much more sensitive to blue than purple. So we're going to see that as blue. So you sort of see that this ink business is it's not perfect. It's not perfect like light, but it is a way of getting all these different colors, as you're going to see when you try to do simulation with subtractive colors. So here is one cyan, magenta, yellow simulator. And if we assume white paper, and you're talking about what ink you would put down there, if you put down a lot of cyan, you're going to get cyan reflected, greens and blues reflected. If you then put magenta on, it filters out some of the green, you just get blue. If you put yellow, it absorbs even that blue. So you just get black. There is no light that comes back from that. And these inks aren't perfect, so we actually generally, inkjet printers usually have a black tub too. Well, we can, if you want to make something on an inkjet printer, you have to specify the cyan, magenta, and yellow balances, and that's what you're going to do in this week's assignment. That's it for subtractive light, but I told you I'd talk about this. This is called Benham's disk. Look it up. I'm not going to talk much about it, but the basic concept is it is all black and white, but as it rotates at different speeds, the brain perceives different colors in those lines.